This video is about determining the length of an arc on a circle. So this is called arc length, just like circumference is known as the distance all the way around a circle. So the convention is to call arc length S, just like we call circumference C or area circle. I don't know why they chose S, but S is how we kind of label or identify arc length. So just as I've drawn it in here, our arc can be determined by 2 points, or we can think of it as being determined by some central angle here, theta. I called it a central angle just because it's the angle at the center of the circle. It's pretty intuitive. So conceptually, if we think of taking a pizza and we cut out a slice of our pizza, that slice becomes a fraction of our entire circle, just like this angle here becomes a fraction of the 360 degrees that make up an entire circle, and just like this arc length here makes up a fraction of the entire circumference of our circle. So that means if the slice that we draw in there is a sixth of our entire circle, then this angle here should be a sixth of 360 degrees, just like our arc length S should be a sixth of the entire circumference. So those ratios will always be equivalent. So we can set up a generic proportion and then use that to determine the arc length in any circle. So we have that our angle theta over 360 degrees equals the arc length over our circumference. So, just a reminder, our circumference is 2 pi times the radius of our circle, so I can substitute that into my formula. And now, solving for S, we have that our arc length equals 2 pi r theta over 360 degrees. Now I'm going to do an example of finding the arc length of an arc on the unit circle. So that's just for simplicity's sake, because on the unit circle our radius is 1. As I set this example problem up, I'm going to go ahead and stick with this ratio here, just because I think it's easier to kind of make sense of what's going on for me. So I'm going to set it up as the proportion and not as this formula that we've already solved for S. Now, since my given angle here was 30 degrees, I just put in 30 degrees for theta, and my radius is 1 because this is the unit circle, so I just have an invisible factor of 1 right there. The first thing I'm going to do is reduce this 30 degrees over 360 degrees to 1/12. And now I'm just going to clear my denominator by multiplying both sides by 2 pi, and I get my arc length for this segment here, this portion of the circumference, is 2 pi over 12, so once again that reduces, and I get that my arc length for this little arc on my unit circle, determined by the angle 30 degrees, is pi over 6. Now this pi over 6 number should look really familiar to you, especially in the context of looking at a 30-degree angle, because a 30-degree angle is equivalent to pi over 6 radians. That means that anytime you're looking at the unit circle, the arc length is going to be equivalent to your angle measure in radians. That means if you're given your angle in radians, or say it's an angle that you happen to know the measure of in radians right off the top of your head, so for example 90 degrees is pi over 2 radians, then you automatically know that arc length. So just to reinforce that, we know that our angle pi over 2 is a quarter of our whole circle, and our arc length is going to be a fraction out of 2 pi, because the circumference of our circle is 2 pi. So when we solve for S, we get 2 pi over 4, and that's the same as pi over 2. So it's always going to work out. So you may be thinking, oh, that's fine and dandy for the unit circle, but how often am I actually going to be working with the unit circle? Well, that's a very good point. So I just want to remind you that where we came up with the radian measure was by mapping out the distance of the radius along our circle. So essentially, whatever our radius is just scales our entire circle up, and the same thing works with arc length. So for this example, I'm going to say my radius is 3. And I'm also going to go ahead and label some of the angles on my unit circle. So remember, 180 degrees is pi, because the entire circle here is 2 pi radians. So if this is pi, if I stop at 90 degrees here, that's just going to be pi over 2. And then this angle, this last quadrantal angle, I'm going to call it 3 pi over 2. Because this is 1 pi over 2, this is 2 pi over 2, and this will be 3 pi over 2. Now, I want to work with a 45-degree angle, so I know that that's just going to cut this angle here in half, this 90-degree angle. So then this is pi over 4, because I've literally just taken my pi over 2 radians and cut it in half. So that's pi over 4. So I could think of this as being 1 pi over 4, 2 pi over 4, which reduces to pi over 2, and then 3 pi over 4 would be right here, and then 4 pi over 4 gives me just pi after I reduce. So now my radius here is 3, and the way I determined this was, so I know this is 45 degrees, but it's also pi over 4 radians, and I want to know what is this arc length. I'm going to do the same thing here and set up my ratios again. So you know 45 degrees is going to be 1/8 of my entire circle, so that's the same as having 45 over 360, that's the same as 1/8 of my whole circle. And that's going to equal whatever my arc length is over 3, because that's my radius, times 2 pi. So when I solve for s here, I get that s equals 3 times 2 pi over 8. Now I'm just going to reduce the 2 over 8 part here. So I get 3 times, I'm going to stick my 3 out in front, pi over 4. So, just like I expected, we have our pi over 4 here, because that's our angle in radians, and then it's just scaled up by a factor of our radius, which happens to be 3 in this case. So, in the event that our radius was 7, I could just replace this 3 here with a 7. So then this 3 here would just be a 7, and I would just have a factor of 7 out in front. So this is one of those examples of a case where using radians makes things so much simpler than trying to work in degrees. Now, I just want to tell you one last thing with regards to finding arc length. So you may be thinking, hey, this is so much easier to do in radians. Why don't I convert my degrees to radians and then find my arc length? But if you set up the problem like I did in the beginning, when I was working in degrees, you have your conversion factor built in. So it's not necessarily going to save you any work to convert to radians and then solve for your arc length. I'll show you what I mean. So this was the general proportion that I set up to start with. So when I solve for s, my arc length, I get that arc length equals 2 pi r times theta over 360. Now I can reduce that 2 over 360, and I get that 1 pi r theta over 180 is my arc length. Now I want you to notice, our conversion factor to get from our angle in degrees to radians was pi over 180. So I can rewrite this, and it's pretty explicit. Here we have our conversion factor times our number of degrees times our radius. So that literally, this right here, I'm going to circle it in the light blue, is our angle measure in radians times our radius. So when you set up your problem using this proportion for the degrees, your conversion factor is built in there. So you're essentially converting to radians anyway when you set it up this way. So it's really not going to save you any time to convert to radians and then find your arc length. However, it's really cool if they give you the angle measure in radians, because then you can just look at it and say, hey, my arc length is just going to be my angle measure in radians times the radius. So, just as a quick reference, this is a unit circle filled in with both the degrees and radians and the coordinates of the points on the unit circle.